one announcement before we begin. The conference photo will take place at 11 today. So, although you desperately want to rush for coffee, with a slight pause first for a photo. Okay. It's a great pleasure to introduce Benjamin Beeker from University of Haifa, who's going to speak to us about cubical accessibility and bounds on curves on surfaces.
So, thank you very much. Can you hear me? Yes. So, thank you very much for the invitation. I'm going to talk about cubical accessibility and bounds on curves on surfaces, and it's a joint work with Nir Lazarovich. So I'm going to start with the second part of the title, and there's a very natural question and answered question, which is you take a surface and you want to put a bunch of simple closed curves on it so that disjoint simple closed curves. So something like this. And of course we know that we can do this until the surface is split into pairs of pans. And so we have a natural bound on the number of curves that we can put on a surface of a certain genus, which is given something by 3g minus 3. So whenever we put a bunch of surface, we're bounded by the topology of the surface. And so we can look at the same kind of problems, for example, for three manifolds. So given the three manifolds, I'm going to draw the same way. How many embedded surfaces can we put that are going to cut this surface so that no two surfaces intersect? So this question has been answered in the case of embedded spheres by Kneser. So that finds a bound on the number of incompressible spheres that are not parallel. So do I have a precise statement. So it's called the prime decomposition. Of a manifold. So when you have a manifold M, a three manifold, and you take S, a set of two spheres that are essential and call it independent. So independent means that they are not translate in some ways of each other's. Then the number of elements is S is bounded by constant that depends only on M. So and more generally, this question has also been answered in the case of surfaces. So instead of looking at spheres embedded in the three manifolds, we look at general surfaces, and so this has been answered by, it's a theorem of Haken, that the number of surfaces that we can embed is also bounded. So given a surface M, a compact irreducible three-manifold, so then we have a bound C depending only on M, so that if S is a set of n surfaces that are disjoint, so closed and incompressible, and also non-parallel, then n has to be less or equal to Cm. So those are very well-known results. I have. And a natural question is what happens if instead of asking, so in the case of surfaces, what happens if in case of asking for simple closed curves, we ask for more general curves, still closed, not necessarily simple, and we allow to intersect. So if we do this, we can draw any set of closed curves that we want. We don't have bound. So what's the natural condition that we should ask on this set of curves to see if a bound exists? So associated to a splitting like this to a set of curve, we have a natural action on a tree, which is given by, if we take the universal cover of this surface and find that, and we lift all the curve that we have. So we get a set of lines on H2, and associated to this, we can build a tree so that each region bounded by those lines is going to be a vertex, and each line is going to be associated to an edge. And so we have that all, and we have an action of the pi 1 of the surface on this tree. And so another way to ask a bound on this set of curve, to see this bound on this set of curve, is to say that the pi 1 acts on a tree that has at most n 3j minus 3 orbit of edges. So for actions coming from a splitting. And so more generally, if we have a set of more complicated curves that intersect each other, or that can also self-intersect. I don't know what this is self-intersecting. We can lift our set of curve on H2, and so this time the curves are going to be intersecting, but there's a result of Sagiv that says that we can there's a natural cat-0 cube complex. So there is a natural cat-0 cube complex on which the group, so in this case it's the group of the surface is going to act. So whenever we have, so in my picture, we don't have more than like two curves intersect. So two curves always intersect one, but we never have a triple of lines that pairwise intersect. So in this case, we can see easily the cat-0 cube complex because it can be drawn the same way as here. We just take a vertex for each bounded region, an edge for each line, and we get a square complex. So that's the construction, but in case of more complicated intersection, then the cube complex is not as visual as it is. And so what we have is to a cube, a d-dimensional cube, is associated by d pairwise intersecting curves in this case in H2 in the case of surface. So our a natural hypothesis to ask is what happens if our set of curve is associated to a d-dimensional cat-0 cube complex. So formulate like this: is there a bound on a set of curves so that are not necessarily simple, such that the cat-0 cube complex associated to the set is d-dimensional. So the bound here would depend on the surface and of course on the dimension. And so that's the question in the case of surfaces, but we have exactly the same kind of construction here. So in this case, we take the universal cover that's going to be H3, and we have surfaces that are going to be H2 embedded in H3. And the same construction of Sagiv applies, and we have an action on the cat-0 cube complex, and we can look at the dimension that's gonna be the same notion of pairwise intersecting hyperplane H2s. So that's such a set of curve on a, let's say on a surface. I'm going to call this a D pattern. So and so maybe a first step can be, in the case of surfaces, to look at what happened for a 2 pattern. So what happened for 2. So for 2 patterns, as I said before, so the cube complex is really visual. So we have our surface and some set of curves. And we can draw our curve complex of our CAD0 cube complex on it. I'm not very good at drawing it, but each intersection is gonna give us a square. And so actually in this case we can see that we have a bound which is given by the Euler characteristic of the surface. So we can cut our surface along curve, and we look at each piece. We can calculate the Euler characteristic, and we see that the number of pieces that are big enough has to be bounded, and so that's going to give us a bound on the number of curves. So that's that's a trick that works in dimension 2 for surfaces, but that cannot be generalized to a higher dimension. So okay, so now I'm going to ask a more general question. So in the case of surfaces, how do we do to bound the number of an easy way to see that we can bound the number of curves is, so we take a triangulation of the surface. We take the universal cover, and we get some kind of lift like this on the universal cover. And what happens is that in order to not to be parallel, two curves have to be separated by a vertex. So when you see a triangle, the way I should use a color. The way you can see the curves are like this. There's no other configuration, and so from the picture you have in one triangle, those two edges are parallel. Those four are going to be parallel, and those four are going to be parallel. But you know that those two are not, and the same for. So everything that's around the central central part of the triangle are not going to be parallel. So on the surface, once you have a triangulation of the surface, you can count how many curves are going to be separated by this center, and that's going to give you a natural bound on the number of curves that can not parallel that can be drawn on a surface. So this is a result from Dunwoody. So he does it in a much more general setting. Is you take so G finitely, let G be a finitely presented group, and you take X, a presentation complex, and you take, so what I define as one pattern, and let P be one pattern. So in the case of general presentation complex, what's going to be, so one pattern is just a set. So in the case of surface, is just a set of curves on my surface. Here I'm looking at things that look like a curve on each triangle, and whenever I have a fork like this, I want to see the curve split. So it's whenever so this is called a track. Whenever a track reaches a new triangle, it continues on this triangle. So if I take a presentation complex and P one pattern, then the number, so this is called something like this is called a track. So I can have many tracks. So the number of tracks, so on X in P is bounded by a constant constant C depending only on G. So that's result of Dunwoody. And so we have a similar result. So maybe I should say, so everything that I said about building a Kazier cube complex, you can do it in the same with this new setting. So if you take X representation complex, and you take a set of tracks, and so P a set of tracks, you can look at the universal cover of X. So this time it's going to be something more complicated, but the lifts of the track are always going to be something that's going to split into the universal cover. And so using Sagiv's construction, that associated to P is going to be an action of the pi1 of X. So G equals pi1 of X. So we're going to have an action of G on a Kazier cube complex, and we have the same notion of dimension. And so we have a notion of D pattern. So a D pattern is more generally a set. So is a set of tracks such that the Kazier cube complex associated is of dimension D. And so so we have a generalization of Dunwoody's result. That says that if we take G a finitely presented group, and we take so X is presentation complex, so here I forgot just to say the number of non-parallel tracks on X is bounded. Of course, if you can take many times the same track, and you don't have a bound. And P a D pattern on X, then the number of tracks in P is bounded. by a constant. C that depends only on the group and on the dimension. So in the case of surfaces, it's just taking closed curve, and so we have a bound on the number of curves that generate a D pattern. So here, so in the case, if I rewrite this in the case of surfaces, so for here a track is just a closed curve. And so we have, that gives a bound on the number of curves in such on a surface given by this configuration. So we have this way of from a pattern to get a CAD0 cube complex. We actually have a way to go the other way around. So so we have, so Sagiv's construction so it's given a pattern, we can get a CAD0 cube complex, and there's a construction from Dunwoody which is given a CAD0 cube complex, we can obtain a pattern associated to it. So the construction is the following. So we have our CAD0 cube complex, somewhere, and we take with an action of G on it, and we take X, the presentation complex of G, and we can create a G equivariant map from X, so from the universal cover of X into our CAD0 cube complex in a very simple way. We fix a vertex. For each vertex, we fix an image, and so I have my for each orbit of each vertex in an orbit, we fix an image. So I have my my simplicial complex, which is the presentation complex of G. I decide to send those three vertices to those three vertices, and then I just connect them in a natural way. and I can extend it to the whole presentation complex. So now I have an image of the universal cover of my presentation complex and my Cat-0 cube complex, and I can look at the hyperplanes of my cube complex inside my cube complex, and they're gonna cut the image of my presentation complex. So here I have one here. This one is gonna, and so I can pull back those intersections. So in this case, I have three hyperplanes. Let's say it's going to be something like this. And so the pullbacks, of the hyperplanes in green are actually going to give me a pattern. So always. And very naturally, so this pattern is so a D pattern. If the Cat-0 cube complex, it's called the Cat-0 cube complex C, if C is of dimension D. So to be more exact, the dimension can go down, but it cannot go up. So yeah, so this construction, so that's a construction from Dunwoody in the case of trees. So it's called a resolution, and so Dunwoody did this in the case of a tree. So in the case of a tree, the hyperplanes are just the midpoint of the edges, and the pattern you get is a one pattern. So is a set of non-intersecting, not intersecting tracks. So this construction, so it's a way to go the other way around, but it's not an inverse. The thing we get, and if we do the two constructions, so take a Cat-0 cube complex, you create your pattern P, and then you do the construction you do the construction again. You don't go back to C, but what you get is a G equivariant map from our new cube complex to our to the one we had at the beginning. And so the question now is, so what do we have here? So we take any action of a group on a cube complex. We get a new cube complex with a J covariant map, and our theorem tells us that in this cube complex we have a bound on the number. So we have a bound on the number of tracks in the presentation complex, and so here we have that gives us a bound. So the number of orbits of hyperplanes so is bounded. So by the same constant by a constant that depends on the group and the dimension. And so a natural question to ask is, do we get a bound on the number of hyperplanes in C? So is there a bound? Here. So in the case of trees, there are several results already known. So we know that, first of all, it's not true in general. So if not true. So it's again Dunwoody. Actually, Dunwoody gave an example. So actually, Dunwoody's example is not exactly in our setting because it's for a finitely generated group. But so here it's an example of an action of a group that can act on a tree with as many edges that you want, and the edge stabilizers are finite. So of action on trees with finite stabilizers, edge stabilizers. So with unbounded number of orbits of edges. And there's also a counterexample from Besvina and Fain, who give an example. So give an actions of F2 on trees, Tn, with I think it's also F2 stabilizers. So it's another F2 edge stabilizers. And with a tree Tn that has n orbits of edges. So the result, the question cannot be answered by the positive in the general case. However, so both in the same, not in the same articles, but the same authors give some positive answers. So in the case of finitely presented group, so Dunwoody says if G is finitely presented and act on a tree with finite stabilizers, with finite edge stabilizers, then the number of edge orbits is actually bounded. Then a bound exists. And more generally, Justina and Fein proved that it's still the case when we replace finite stabilizers by small stabilizers. The small, you have to see this as not containing F2. Not exactly the definition, but okay. So those are the positive results. So then a bound exists. In this case too. And there's another similar result with by Sela. So that doesn't put a condition of the stabilizers, but that puts called acylindricity condition. So that says that if G, a finitely presented group, acts on the tree T, that is so K acylindrical, so what does K acylindrical means? It means that the stabilizers of an edge E and an edge E prime is empty, is the identity. Whenever E and E prime are at distance greater than K. And so in the case of when the action is acylindrical, then there is a bound on the number of orbits or bits of edges. So the bound here depends on G, and of course depends also on the K ascendrical constant. And so with near, we are able to extend this this result because so we have the same result. So so we take G that is finitely presented, and let's act on a d-dimensional K0 cube complex. K, so hyperplane ascylindrical. So it's the same condition, but you replace edge by hyperplane. So intersection intersection of stabilizers is empty whenever the distance is greater than K. So distance meaning you have K hyperplanes in between them. And so then the number of orbits of hyperplanes is bounded by a constant that depends on the group, on the dimension, and on K. And so this and so this this theorem is a consequence from so the previous theorem and the construction of our G equivalent map. Which is as follow. So here you assume that G is K ascylindrical, and you make this construction. So now, this construction comes from our pattern in the presentation complex. And so if there are too many hyperplanes here, we know that when we're going to lift our set, when we're going to make our construction, we're going to have too many hyperplanes there. We're going to have too many tracks there. So there must be some parallel ones. And if there's really a lot, then that means we can find K hyperplanes that are parallel. And those k hyperplanes that are parallel are gonna become tracks that are parallel here are gonna become hyperplanes that are parallel there. Now there's the pi1 in our presentation complex. The pi1 of the track is the stabilizer of this track, and therefore it's a stabilizer of the hyperplane. And so the intersection of the stabilizers of those two is not trivial. And what we obtain is so we have the same here, and we can push it back there and find two hyperplanes that are far apart and that have non-trivial intersections. So that's a contradiction. If we have too many hyperplanes there, we have a contradiction. Okay, I think I'm going to stop here. Thank you.
Any questions?
I thought Zell's theorem was for finitely generated groups, right? But we have it with finitely presented. Am I
I
wrong?
haven't given the same proof.
Yes, sure. That's
Yeah,
why
that's
I'm wondering.
And there's a missing assumption of one-ended.
Okay, so you also do it for finitely generated. No. You do it for finitely.
This is for finitely presented in our case, yes. So you're probably right. It's finitely generated in the case of Sena.
So you don't know it for finitely generated in your setting.
So it's I didn't say it, but this is a generalization. So in the case of trees, there's a proof of Céleste's theorem. So this time in the case of finitely presented by Delzon, which is the same proof. Yeah, sorry. So probably Céleste is finitely generated, and Delzon does it. It's a simpler proof in the case of finitely presented. Yes. So this is a generalization. I should say it. So this proof is a generalization of Delzon's one.
Any more questions? Okay, let's thank the speaker again.